Chapter 8 continues with this video. Here are the diverse reactions of alkenes that are discussed in this chapter. So far we have seen the conversion of an alkene to a halohydrin, to a 1,2-dihalide, to a halide, and now in this video I will show you how we can convert an alkene to an alcohol and an alkane. And here is a picture of Dilly outside in the sunshine. Acid-catalyzed hydration involves the addition of H and OH to a double bond. H and OH make up water, so this is called hydration. And it also follows Markovnikov regioselectivity. So here, the carbon with the double bond that has more H's gets the H of the HOH, and the OH goes on the other carbon. So this had one H to begin with, and now in the product it has two. The second hydrogen came from water, and then the OH is on the other carbon. Sulfuric acid is typically the acid catalyst used. So the OH is added to the more substituted carbon of the alkene, and the more substituted the carbon atom is, the faster the reaction. So with just ethylene, the relative rate would be 1, but by adding one methyl group onto the alkene, the rate of the reaction increases a millionfold. So this reaction is a million times faster than that reaction. And then there's a further increase to a relative rate of 10 to the 11 by adding a second alkyl group to the alkene to make it disubstituted. So the disubstituted is hydrated 10 to the 11th times the rate of ethylene, which is 100 billion times faster. So here's my question for the chat. Is this data consistent with a mechanism that proceeds through a carbocation intermediate? And here is the mechanism. You can see if you were correct in your analysis. So it's essentially the same as hydrohalogenation. In the first step, the alkene is protonated. So we draw an arrow from the pi bond to an H of H3O+. And then we form a carbocation intermediate. And then water attacks in the second step. So we've got nucleophilic attack. So we draw the arrow from the lone pair on the oxygen to that positively charged carbon. Now, after the water attacks, we still have a positive charge on the oxygen called an oxonium ion. So a second water molecule must deprotonate that. So our final step is a proton transfer, which gives us this product. Here is the animation of the hydration reaction. So there's our double bond. It gets protonated. The H goes on the carbon with more H's, and we form a carbocation intermediate, which then the water as the nucleophile attacks, forming a CO bond. And then finally, another water molecule deprotonates the oxonium ion, and we get our product. Notice we regenerate H3O+ in the process, so this is catalyzed by H3O+. The reactants and products of hydration are in equilibrium, and we can exploit Le Chatelier's principle to control the direction of the equilibrium. So if we use dilute H2SO4, so we have more water, then the equilibrium will favor the products, because Le Chatelier's principle says that you shift the equilibrium away from the reagent in excess. So if we have a lot of this, the equilibrium will be shifted in this direction. If we wanted to go backwards from the alcohol to the alkene, we would use less water and concentrated sulfuric acid. Just like with hydrohalogenation, if you form a chiral center, you're going to get a mixture of R and S. And why is it we get an equal mixture? Why don't we just get R or S? So think back to why we would get a mixture with hydrohalogenation and discuss this in the chat. Now, the acid-catalyzed hydration I just showed you actually has limited applications because since it goes through that carbocation intermediate, rearrangements can take place and then you get a mixture of products. So there is another reaction that's much more commonly used, but it's a little more complicated. And it's the oxymercuration demercuration. And you're only going to learn part of the mechanism because the second part is quite confusing for this level of organic chemistry. So in the first step, you're going to add mercuric acetate, HgOAC2. So OAC, so this would be mercury 2 acetate. So the OAC represents this group. And that's going to form a mercurinium ion. So like with the addition of a halogen, we formed a halonium ion. We're also going to form a 3-membered ring with mercury in the middle. And then water is going to add to that intermediate, opening up the ring. And then sodium borohydride, which is a boron with 4 hydrogens attached with a negative charge. That's going to remove the mercury and replace it with a hydrogen. So first of all, the active mercury species is actually this species with just one acetate, that's called an acetate group, on it. So this is the reagent you would get off the shelf and you would add to your flask, but in solution it's going to be in equilibrium with these two forms, and this is the form that's going to be active. So in the acid-catalyzed hydration, the pi bond was protonated and we got a carbocation which could rearrange. However, in the oxymercuration demercuration reaction, the alkene will add to the mercury atom, and immediately that adds to the other carbon of the alkene, forming this mercurinium ion, which will not rearrange. And that mercurinium ion can be easily attacked by a nucleophile, and it will be attacked on the more substituted side, just for the same reason we saw with the halohydrin, and that side is going to have a buildup of positive charge because that can be more stabilized by the additional alkyl groups. So the nucleophile attacks at the more substituted side here. So that opens up the ring. So the nucleophile attacks, we break that carbon and mercury bond to get to this intermediate. And then sodium borohydride will replace this entire group with an H. So the two reaction sequence using oxymercuration demercuration provides the same product as acid catalyzed hydration, but without rearrangement. So if you had instead used just acid and water, what products would you have gotten here? The next type of reaction is called a hydroboration oxidation. It also takes an alkene to an alcohol, but it does so with anti-Markovnikov regioselectivity. So this is the first time we're seeing anti-Markovnikov selectivity. So here the H goes on the carbon with less H's and the OH goes on the carbon with more H's. And this is a two-step reaction sequence. So in the first step you're adding BH3THF, and in the second step you're adding hydrogen peroxide and sodium hydroxide. BH3 is borane. It is a boron with 3 hydrogen atoms, and it has an empty p orbital. So when you put it in a solvent like THF, which is tetrahydrofuran, it actually complexes the empty p orbital of the boron complexes with the lone pair on the oxygen. So we call the whole thing BH3THF. The regiochemistry that results is very helpful when you have an unsymmetrical alkene. So for example, if you start with 1-methylcyclopentane, the product you get has the OH on this carbon and the new H on that carbon. And the OH and the H are going to add from the same side. And since they add from the same side, that's called syn stereochemistry. So again here, this shows another reaction with BH3THF where the OH and the H that have been added are added in a syn fashion. And again, if you create chiral centers, you will get a mixture of enantiomers. So the anti-addition where the OH and the H are on opposite sides is not observed. Hydroboration follows anti-Markovnikov-Regio selectivity, and the reason can be determined by the mechanism. So in the first step of the mechanism, the alkene adds to the borane, where an H, which is the smaller atom, gets attached to the more substituted carbon, and the boron, which is much bigger than H, goes on the less substituted carbon. And the reason for this is sterics. The small, tiny H atom can more easily fit and bond at the carbon that's more substituted, and the much larger boron atom would prefer to be attached and approaching this carbon where there's a greater ease of accessibility. So then you get to this intermediate where you have a hydrogen on the carbon that was more substituted and a BH2 group on the other carbon. And we want to use two arrows to show this. So one arrow going to form a bond with the boron, and another showing the hydrogen forming a bond with the other carbon of the alkene. So here again we see another addition, and we see the boron is going to attach to the more sterically accessible carbon, the one that's less substituted. This is not formed because you have that methyl bumping into the boron. And then after addition of hydrogen peroxide, you get the final product. And the second step, which you will not learn a mechanism for, is using hydrogen peroxide and sodium hydroxide. And in that, you replace the BH2 group with an OH group. If you want to know the mechanism for that step, I'd be happy to show it to you, but it's quite complex and I'm not requiring you to know it. Then the final reaction in this video is catalytic hydrogenation. So with hydrogenation, we're adding H2 to a double bond. And notice we're starting with an alkene and we're ending with an alkane. This requires a metal catalyst. And oftentimes when we're doing these alkene additions, we refer to things as being added across a double bond. So you may see this terminology a lot. Without a metal catalyst, the addition of hydrogen is too slow due to a very high activation energy. But with the catalyst, it can proceed in a reasonable time frame. This reaction is stereospecific. Only syn addition is observed where the H's, both of them add from the same side of the alkene. And again, if you form chiral centers, you'll get both enantiomers. The metal surface binds the hydrogen and the alkene. They both get adsorbed to the metal surface, which facilitates transfer of the H atoms to the pi bond and also explains why the addition forms in a syn fashion. This animation is going to show how that works. So we have an alkene and a hydrogen molecule, and they're getting adsorbed to the metal surface. And then the hydrogen splits into two hydrogen atoms, which then attach to the alkene. The syn addition of hydrogen to a symmetrical alkene will not produce a pair of enantiomers because a meso compound is formed. So while yes, you can get both enantiomers, if you end up with a meso compound, well, that's actually the same compound just flipped over. So the exception to the rule that you'll form enantiomers is if you happen to form a meso compound. Now test your understanding. So can you figure out the product of this reaction? Is it 1, 2, 3, 4, or 5? So this is our oxymercuration demercuration set of reagents. Think about it and put your answers in the chat. Now look at this reaction, and instead of the mercury acetate reagent, you're using BH3 followed by peroxide. And which product would that give you? Put your answers in the chat. If you reacted this alkene with hydrogen and palladium, so palladium is the catalyst, PD over C means it's palladium on carbon. What product would you get? Draw out the product, name it, and put the name in the chat. Finally, what alkene would yield 3-methylpentane upon subjection to catalytic hydrogenation? So I'm giving you the product, and now I'm asking you what would the reactant be? Which of these alkenes would be the reactant? Which of these, if you reacted it with H2 and a metal catalyst, would give you 3-methylpentane? So first figure out what 3-methylpentane looks like, and then work backwards.